if you've seen the movie Ratatouille.
Ratatouille?
It's about a mouse who likes to cook. He's sitting around making soup. You can think of it as like adding salt to your soup. Salt is not necessarily a good or a bad thing, but if you don't have enough salt in your soup, it doesn't taste very good. But if you add too much salt to your soup, it actually tastes terrible too. And so it's about adding just the right amount. And I think of doing mineral enhanced rock weathering the same way. Adding these minerals to the ocean is not necessarily good or bad. The earth is doing it naturally anyway. But if we do it too much, we might tip that balance towards something that isn't environmentally safe. So it's about doing just the right amount that we get the climate benefit without negative environmental impacts. Not too much, not too little, but something that's both effective for carbon removal, but also safe.
Basically building up the trust in the very nascent industry so that everyone will understand the science of making a soup and how not adding too much salt into the ocean.
You're listening to Bite-Sized Climate Tech, Season 4. Let's dive in.
Time to make climate cool again.
Hi, Grace.
Hi, Lydia. Thanks so much for having me.
Thanks so much for coming to the show. So happy that you can join us today. Grace Andrews is a scientist in the Earth and Planetary Science realm. She used to be the head of science at Project Vesta, and now she's the founder and managing director of the nonprofit Hourglass Climate. If you want to add something about yourself and what you're working on.
Yeah, like you said, I'm the founder and executive director of Hourglass. We are a US-based nonprofit organization working on a class of carbon dioxide removal technologies called ocean alkalinity enhancement, and specifically within that mineral-based ocean alkalinity enhancement strategies. So we do research on these really to support the responsible development of this industry, including tool development, but also field trials.
And that's why today we're going to talk about this very exciting topic that you're going to tell us about ocean soup. How do you get the recipe right for the ocean carbon removal and minerals that people use to add into the ocean to help us remove CO₂?
Yeah, fundamentally, the way that this works is we add alkaline rocks and minerals to the ocean. And there are lots of ways to do that. Sometimes it's called marine enhanced rock weathering. Sometimes it's called ocean liming or river liming or coastal outfalls. But at the end of the day, we're adding these minerals to the ocean where they can very gradually dissolve. That dissolution process ends up generating alkalinity, which is a dissolved form of carbon. But what it really does, why this matters for climate, is it ends up creating what I think of as like a CO₂ deficit in seawater. So seawater, the surface ocean, is constantly exchanging CO₂ with the atmosphere, and it's in what's called equilibrium. When you create this deficit in seawater, it drives CO₂ from the atmosphere to go back into seawater, flux into the seawater to fill that hole and reestablish equilibrium, which is how we end up net taking CO₂ out of the atmosphere.
When I first got into carbon removal, I always think that there's a one-on-one comparison between the things on the land and the things in the ocean. So I just learned from you before we got on air, you said that the enhanced rock weathering on the land, you add some kind of minerals to the soil. Is it marine ERW is part of the ocean alkalinity?
Yeah,
enhancement?
It's an ocean alkalinity enhancement. Mm-hmm.
It's a part of ocean alkalinity enhancement. And when you're trying to make it correct and right for the ocean, it's as if you're making a soup so that it has the perfect mix for the atmosphere to reach the equilibrium.
Yeah, the way I think about this is when you're dissolving these minerals, all rocks and minerals are actually made up of a whole bunch of different elements. And so when you dissolve those rocks and minerals, it's adding things like silica to the ocean or magnesium or calcium, things that are already like super abundant in seawater. But we're also adding alkalinity, also abundant in seawater, but we're adding more. And we're adding all these rocks and minerals also have just very small amounts of a bunch of other sort of what we call trace elements. So that can be things like nickel or cobalt that are there in just really small quantities. So we also end up adding those to the ocean. Those elements, they're also already existing in the ocean. And actually things like nickel are micronutrients. So they're essential for life. But when we're doing and thinking about these kinds of interventions, we have to think really carefully about making sure that we're adding just the right amount. like not too much, not too little, but something that's both effective for carbon removal, but also safe.
In the ground, they measure some kind of elements. They don't measure all the minerals, right? Is it the same when it's in the ocean? Like all of those minerals, what do you measure to measure how much CO2 is being removed?
I mean, you can use these trace elements to actually quantify how much of that mineral has dissolved because, the background amount of, we'll say, nickel in the ocean is pretty low. And so you can measure any additional nickel above that. And it's really only coming from one place. It's coming from the minerals that you've added. By looking at that difference, you can actually get a really good understanding of how much of your mineral has dissolved and therefore how much carbon you're removing.
Got you. So there's a direct relationship between how much you can see that the minerals you added is being resolved to the CO2 being removed. Okay.
Just measure alkalinity. That's the other nice thing. You can look at it. You can measure the increase in alkalinity too. It's a really nice system because you can track sort of both sides, how much mineral has dissolved and how much alkalinity has been produced. And so you end up with really high confidence actually in your carbon removal.
How would you explain this to an 8-year-old?
You said that you have an 8-year-old yourself.
I do have an 8-year-old, so I'll just tell you how I explain to him what mom does at work every day. This process of dissolving minerals to take CO2 out of the atmosphere, this is a process that already controls Earth's climate over sort of the million-year time scale. This is how it happens. What we're doing for marine enhanced rock weathering, basically we're just doing the process that's already happening anyway, but we're grinding those rocks and minerals up into really small particles so that the reaction happens faster. And it happens on a time scale more like our lifetime rather than millions of years. So we're working with Earth's natural carbon cycle.
You first laid the groundwork of telling the kid how the ocean is working with people adding these minerals. If you think about put it in a day-to-day scenario so people can picture it.
I think a great example, I don't know if you've seen the movie Ratatouille.
Ratatouille?
It's about a mouse who likes to cook. He's sitting around making soup. And I think this is where this idea of like the ocean soup comes from, right? You can think of it as like adding salt to your soup. Salt is not necessarily a good or a bad thing, but if you don't have enough salt in your soup, it doesn't taste very good. But if you add too much salt to your soup, it actually tastes terrible too. And so it's about adding just the right amount. And I think of doing mineral enhanced rock weathering the same way. Adding these minerals to the ocean is not necessarily good or bad. The Earth is doing it naturally anyway. But if we do it too much, we might tip that balance towards something that isn't environmentally safe. So it's about doing just the right amount that we get the climate benefit without negative environmental impacts.
Thinking about the soup, I love good food. I think it's also when you say that you wouldn't just add like rocks into the ocean, right? It's as if when you're cooking, you're not going to add like a whole bulk of salt. You need to like grind it in a smaller granular way so that you can add it to the soup and then you make it as a right balance. When you actually drink the soup, it tastes perfect and it reacts with some other spice and other nutrients and, delicious ingredients.
And you're totally right about the reason like salt dissolves faster in soup when it's ground up really fine and when you're doing it when the pot is boiling, right? And when the water's warm. Same way with marine enhanced rock weathering. It works better in warmer temperatures because the rocks dissolve faster and it works better when the grains are small. So it's exactly the same.
Oh, I didn't know that. That's a fun fact to know of today. Great. Now we're going to move to the next segment, which is you're going to answer a question from a previous guest. Her question is, what strategies are you using to overcome any challenges getting your climate tech solutions out there? Because every climate tech solution is really groundbreaking, but it also comes with a lot of resistance. How do you face those challenges?
So I think for our technology, marine enhanced rock weathering, like I said, the main challenge and the main concern from stakeholders generally is this side of environmental impacts. So how do you know you haven't added too much salt? And so something that we're doing at Hourglass to overcome that is we are building what we're calling the framework for ecotoxicological modeling of MCDR, which is basically like a guidance document, a process-based document to help actually quantify numerically the environmental impact of a proposed project. It's a way to take the guessing out of it and to add a lot of rigor to actually how we assess the risk of a project and make sure it's not too much salt. This is something we've been working on for a while. I'm really excited about it. Our vision is that this actually gets incorporated into MRV protocols to sort of improve what sometimes people think of EMRV, environmental MRV, and actually get just as quantitative about environmental impacts as we do about the carbon removal. So that risk benefit analysis is really rigorous. We've written it. We went through a public comment period actually quite recently, and we're revising it based on those comments. We got a lot of really positive feedback, which was exciting from across the industry. So yeah, we'll be releasing it by the end of the year.
This is very good news. I think it's basically building up the trust in the industry, in a very nascent industry, so that everyone understand the science of making a soup and how not adding too much salt into the ocean. Can you leave a question for the next guest?
Something that I think about a lot, I'd love to learn about is how the sort of current political landscape is affecting the development pathway for your technology, if at all.
I always ask my guests, why did you decide to work in climate?
I am working in climate because I truly believe that this is really the greatest problem of our lifetime. There is nothing more important that I could be using my brain, my talents, my resources to be trying to solve. This is an existential problem for our environment, for human health, for the economy, everything in between. And so if this is a nut we can crack, then this is something that is certainly worth my time.
You started pretty early though, more than a decade ago, right? What was the trigger? Because now it's like everyone wants to work in climate, but it's not the same 10 years ago or more than 10 years ago.
Yeah. I mean, I was always interested in, climate change and understanding what I could do for climate change. Honestly, it's maybe a little cliche, but back in high school, that's when I saw like An Inconvenient Truth, Al Gore's movie, and I found that generally really inspirational. And I went to college and I started studying the carbon cycle in college. I like to say I've been working on carbon removal before it was cool. I have to tell you, I love my PhD advisor. He wasn't necessarily sold on me working on enhanced rock weathering when I started in it, but times have changed. He works on it now too. So there we go.
Oh, great. Turning the tides. Yeah, this is the second time someone mentioned about the movie. That's the trigger point for them to start working in climate. We have a closing tradition is you're going to leave one sentence of hope for our audience.
What I find truly, truly motivating and inspirational is actually sort of what we just talked about, is this really constant upward tick in interest, in financial commitment, in scientific rigor around actually advancing carbon dioxide removal technologies. It is a completely different world today than it was 10 years ago, and that's a great sign.
If you summarize in one sentence is, with enough people and attention, we can turn the tide.
If we keep working on carbon removal at this sort of upward trajectory that we have been over the past 10 years, I genuinely believe we can solve this problem. Let's make
climate cool again. Yeah, thank you so much, Grace.